Okay, sir. A very warm good morning and welcome to this August gathering. It is both an honor and privilege for all of us at MIDFT to present a webinar series on reducing carbon footprint in the dairy industry, future and challenges, edition 2. We are honored this morning by the presence of Honorable Vice Chancellor, Kamdhenu University, Dr. N.H. Kelawala, sir.
Good morning.
I also welcome Professor G.S. Rajoria, President IDA, for kindly delivering the keynote address. We fully appreciate you, sir, for finding time to be with us. I also welcome Dr. P.H. Bhattalia, Director of Extension Education, Kamdhenu University, Dr. D.B. Patil, Director of Research, Kamdhenu University, Dr. Vimal Ramani, Principal and Dean, Faculty of Dairy Science, Kamdhenu University, Dr. B.N. Patel, Director of Students' Welfare, Kamdhenu University, Dr. J.B. Upadhyay, Dean, FMC College of Dairy Science, Anand, for the kind presence this morning. On behalf of MIDFT, I warmly welcome deans, faculties, students of different universities, colleges, dairy technologists from different district cooperative milk producers union across Gujarat, dairy experts, and all other distinguished participants for finding time to be with us today. We truly believe that the engagement of faculties from different organizations attending today will certainly make this webinar fruitful and productive. To begin this program, I feel privileged to call upon an idol of knowledge, experience, and the driving force behind this webinar, Dr. Priya Patel, Executive Director, MIDFT, to kindly deliver the welcome address. Sir, please.
Good morning, everybody. Namaste, and we welcome you to this series of webinar of reducing carbon footprint in the dairy industry, future and challenges we will face in time to come. Edition 2. It is my immense pleasure to welcome Professor Dr. N.H. Kelawala, Honorable Sir, Vice Chancellor of Kamdhenu University, and I wish to inform all of you that now under the umbrella of Kamdhenu University, there are more than 20 colleges and different research stations. So Kamdhenu University has gone stronger under the leadership of Honorable Dr. Kelawala. So we congratulate you all, sir, on this achievement, and we hope that Kamdhenu University goes ahead with the time and becomes one of the prime university of the nation. Welcome.
Thank you. Thank you very much.
I welcome Professor G.S. Rajoria ji. It is our immense pleasure that you have spent your time to be with us today as a keynote speech you will be delivering for this seminar. We welcome you, and it is our pleasure that you are with us. Welcome, Dr. Rajoria. I welcome Dr. Sudeep Tati, who is CEO of the Prompt Innovations Private Limited. He will be presenting us on sustaining cooling solution for Indian dairy industry, Milk-O-Chill and instant milk chiller at source, which will reduce a lot of energy consumption in time to come. We welcome you, Dr. Tati. I welcome Professor Manishankar Das Gupta, HOD Mechanical Engineering Coordinator, IQAC, BITS Pilani. He will be representing carbon dioxide heat pump for waste heat recovery and utilization in dairy industry. We welcome you, Dr. Das Gupta. We also
Namaskar.
Mr. Priyank Mehta, Executive Engineer, Badasari, Palanpur, who have in fact demonstrated how the dung and urine could be used to generate CNG and biogas for utilization of the society as a whole. And they have done tremendous work, and they have been pioneering doing this work. So welcome you, Mr. Priyank Mehta. I also welcome Dr. Javid Parekh, who is an eminent dairy consultant and technical advisor to many of the dairy industries and food industry in nationwide and international also. He is also the CEC member of IDA. We welcome you, Dr. Parekh, that you have joined with us. I welcome Sri Patil, all the dairy cooperatives like Sarag Dairy, Sabha Dairy, Banas Dairy, Panchama Dairy who have joined today. I also welcome faculty of various Kashmir, Tamil Nadu, Assam, Patna, and all other faculty around India who have joined in this webinar. We welcome you all, and I request Binu to please continue with the seminar.
Thank you, sir. We are highly privileged to have the navigator of the flagship of knowledge, Honorable Vice Chancellor, Kamdhenu University, Dr. N.H. Kelawala amidst us. Honorable sir, may I now request you to kindly bless us all with the opening remarks. Sir, please.
Good morning to one and all. Honorable Executive Director of prestigious Institute, MIDFT, Mehsana, Dr. P.R. Patel, sir. First of all, thanks for your compliments, encouraging compliments. Dr. P.H. Vatalia, Dr. D.V. Patil, Dr. B.N. Patel. I can see Dr. Sukla, Principal and Dean MIDFT, Dr. Vimal Ramani from CDS Amreli, Dr. Janak Upadhyay, Dr. B.G. Patel, invited speakers, Dr. G.S. Rajoria, sir, President IDA, he will going to deliver keynote speech. Dr. Sudhindra Tatti, CEO Prompt Innovations Private Limited, Ahmedabad, going to deliver talk on sustainable cooling solution for Indian dairy industry, Milkochil, and instant milk chiller at source. Professor Manishankar Das Gupta, Head of Department Mechanical Engineering Coordinator, IQAC Pilani, going to speak on carbon dioxide heat pump for waste heat recovery and utilization in dairy industry. Mr. Priyank Mehta, Executive Engineer, Banas Dairy, Palanpur, going to speak on bio-CNG plant. Dr. J.V. Parekh, Dairy Consultant, Technical Advisor, Food and Dairy Association, and he is going to speak on energy conservation in dairy industry. I can see Arunbhai Patil, Dr. Punambai Prajapati, faculties from all the state dairy science colleges, students, organizing and coordinating team of MIDFT, Dr. Binu Tanwar, Dr. Ankit Goyal, Mr. Kundan Chaudhary, faculty members, student participants, ladies and gentlemen. First of all, I would like to congratulate whole organizing team from MIDFT for organizing scholastic webinar series on reducing carbon footprints in dairy industry, future and challenges edition 2, of which edition 1 was successfully completed with curious discussion on 1st of September 2020. Now in this second edition, the main focus will be on operation and process is associated with the milk and milk products processing or manufacturing plants and their energy efficiencies and the protocols to be followed to reduce the greenhouse gases or carbon footprints. Major area would be smart and justified use of natural resources like energy and water from alternative sources than the conventional one. I hope this webinar series will eventually assist in the development and evaluation of mitigation strategies for reducing greenhouse gases emissions and improving the overall sustainability of the Indian dairy sector. As you all very well aware that climate change is a global problem, we need to contribute not from the industry, but also from ourselves and from our daily lifestyle. A very hot topic, not only for today, must having concern all around the globe with regards to global problem of climate change and global warming. As you very well know, India is world's third largest emitter of greenhouse gases after China and US. India's gross emission of greenhouse gases were estimated at almost 3,600 metric tons in carbon dioxide equivalent in 2015, of which the energy sector contributes the largest, followed by the agriculture sector. Of the 0.39 billion tons of carbon dioxide equivalent from India's agriculture, about 58%, that is 0.23 billion tons, is from enteric fermentation from livestock, while India's dairy sector accounts for a massive 18.3% of global milk production. Its contribution to greenhouse gases emission is only 14.1%, which includes emissions associated with milk production, processing, and transportation of milk and milk products. Measured per person, India's emissions are still very low, maybe due to this dense population, at only 1.8 tons of carbon dioxide per capita, which is much lower than the world average of 4.2 tons. But those emissions have been growing steadily with an average growth rate of past decade of 6%. The most important greenhouse gases generated by dairy industry are methane, nitrous oxide, carbon dioxide, and some refrigerants like hydrofluorocarbons and chlorofluorocarbons. Nitrous oxide emission is due to production and use of fertilizer, manure storage. Carbon dioxide emission occurs due to the use of energy at farm level as well as processing level. Main greenhouse gas sources at dairy production process are animal farming, livestock management at farm, consumption of fossil fuels in transportation and other purpose, consumption of electricity, use of chemicals at various processes like released greenhouse gases, refrigerant loss from the cooling system, waste disposal and management that produce greenhouse emissions. Friends, non-renewable fuel that are directly engaged for continuation of different dairy operation can be partially replaced by different renewable fuel. That approach directly mitigate the high emission risk. On the whole, reduce carbon footprint. In dairy processing, applications of non-thermal activities instead of thermal activities can be fruitful. Novel approach to reduce load of carbon footprint in dairy industry. Applications of additives could be another future approach for reducing carbon footprint in dairy industry. For an example, for manufacturing of butter, aging steps is required for fat crystallization, and this step requires several hours, and that increase fuel consumption rate. On the whole, increase carbon footprint. Therefore, any additives able to decrease butter aging time that directly reduce fuel consumption for that particular step, hence reduce carbon foot chain for butter manufacturing section in dairy plant. So multidisciplinary approach can be efficient to reduce the load of green gas emission load, moreover reduce the carbon footprint from daily processing industry. I won't take much time. There are learned speakers, and I want that you all should exchange the ideas, and this webinar series will provoke thoughts of dairy technologists, academicians, and especially students who are the future of dairy industry. I request all participants to take active participation in this webinar. Stay safe and healthy, especially during current scenario. At the end, I congratulate team of MIDFT for taking a wonderful initiative. Thank you very much.
Thank you, sir. Thank you so much for sharing your deep knowledge with us. Thanks once again. We are highly privileged to have a seasoned scholar, navigator of the flagship of knowledge, and academician par excellence, Professor G.S. Rajoria, President, Indian Dairy Association, amidst us. Respected sir, may I now request you to kindly bless us all with a keynote address. Sir, please.
Okay. Thank you. I'm very happy to meet Professor Kelawala, Vice Chancellor of Kamdhenu University. Hopefully we will meet again in future, Dr. Kelawala, Professor Dr. P.R. Patel, Professor Shukla, my friends from the Central Executive Committee of the Indian Dairy Association, Dr. Parekh, Mr. Arun Patil, members of the Indian Dairy Association who have joined from different parts of the country, the participants from dairy industry, and dear students. I am privileged to tell you that I am honored that MIDs have invited me to deliver this brief keynote address. You are aware that greenhouse gas emissions to the atmosphere and their potential impact on global climate have become important concerns worldwide. Dairy production has a considerable effect on climate change due to emission of greenhouse gases such as methane, nitrous oxide, and carbon dioxide. The emissions largely come from feed, production processes, as Professor Kelavala said, enteric fermentations, and manure management. I have seen, some information that emerged out from the first webinar in this college that feed production accounts for about 20.3% of the total gas emissions, followed by milk production, processing. Milk production takes 51.5% share of the total gas emissions. Processing takes about 5.7%, packaging 3.5%, milk transport 7.7%, retailing 6.5%, and consumers also equally contribute to gas emissions, which is about 5%. Milk production takes place all around the world. Demand for dairy continues to increase due to population growth, rising incomes, urbanization, and modernization of diets. There is growing pressure, therefore, on natural resources, on fresh water and soils to produce large amount of foods. Dairy animals and their manure produce greenhouse emissions. Dairy operations also contribute to water pollution and soil degradation. Airborne emissions of ammonia can damage species diversity. The output of particulate matter and odor from farm activities can negatively impact air quality. Dairy operations can consume large volumes of water to grow feed, watering for the animals, managing the manure, and process the products. Runoff water from dairy farms can pollute water resources. Increased nutrients in local waterways may contribute to the growth of algae, which reduces oxygen for aquatic plant and animal life. Improper handling of dairy animals decreases the productivity due to stress and ill health and leads to increased greenhouse gas emissions. A more sustainable dairy industry must be developed to reduce environmental impacts across the entire value chain through adoption of measurement guidelines and promotion of best practices. Energy production is the largest source of these emissions. The production of dairy products contributes to about 3.6% of the global planet warming emissions each year. Animal feces and urine are pumped into giant cesspools and liquid waste is spread out onto the nearby fields, creating a fine mist that may pollute the air which reaches the neighboring communities. This is a serious health hazard and a clear example of environmental injustice. According to a report by the UN Food and Agriculture Organization, animal agriculture accounts for more greenhouse gas emissions than the entire transportation sector combined. That's more than all the planes, the trains, and the cars in the whole world. Deforestation and loss of biodiversity has become necessary. It is a loss which is created because of several factors. Grazing lands grow feed crops in countries like that of US may lead to irreversible climate change. It's time we stand for a better world because of if we don't, it won't happen. The green fodder crops are heavily sprayed with pesticides which make their way up to the food chain. According to some estimates, some 90% of the total pesticides which are spread on the field, they find way to soils and the food subsequently. They also kill bee, butterflies, wildlife, the surrounding ecosystem, and threatening exposure to the farm workers. Carbon footprint in dairy industries is measured by greenhouse gas emissions, and their potential effect on the environment has become an important national and international issue. The challenge for policymakers and for the dairy sector is how to reduce environmental impacts while continuing to meet society's needs. With demand for high quality animal proteins increasing globally, the dairy sector is well placed to contribute to global food security and poverty reduction through the supply of dairy products. The world is already experiencing more frequent floods, storms, and droughts. Forest fires causing damage to environment and people's livelihoods. In order to limit temperature rise, the dairy sector must reduce the greenhouse gas emissions and work towards a low carbon future. Emission intensity of carbon dioxide is the lowest, and protein corrected milk in developed countries than in the developing countries. The reason is that the amount of milk produced per animal is smaller than the amount produced per animal in the world. So larger the milk producing capacity, lower will be the gas house emissions. It is important that strategies can involve nutrient recovery technologies like anaerobic digestion to produce nutrient rich manure to replace use of synthetic fertilizers. Research, policies, regulations, infrastructure, and incentives will be required to systematically support low carbon emissions. Investments in data gathering and also in-depth analysis will help identify and refine mitigation options for our actions to reduce the carbon emissions. There are, some latest innovative initiatives which have been placed to practice to reduce the gas emissions, like solar miniatures from a Trivandrum. There is a train, Kochi. We have an international airport totally operated on solar power. Gas house emissions could be reduced by substituting fossil fuels with energy produced from crop residues, dung, energy crops. Use of bioenergy would depend on relative prices of fuels and the balance of supply and demand. Installation of gobar gas plant using 1 ton dung obtained from 100 adult animals will produce about 50 cubic meter of the gas. And the gas that we produce will be now something like 20 kg per animal. This gas can be utilized for thermal as well as power generation, besides producing purified and compressed gas to produce bio CNG for commercial purposes. Gobar gas can be used for heating of milk and water as well as for power generation. The cost of installing a 30 cubic meter capacity gas from 100 to 110 dairy animals will cost about rupees 5 lakhs, with a state subsidy in some states of rupees 2 to 3 lakhs. The Ministry of New and Renewable Energy Sources of Government of India is promoting power generation for grid installation There is also an example. Presently, Haryana Agriculture University is installing 1 megawatt, which is about 1000 kilowatt units to operate electrical appliances through solar energy. A private company is setting up this plant and the entire cost will be borne by the company. The university will get electricity at rupees 3.3 per unit as against rupees 6.4 rupees paid to the Bijli Vitran Nigam. The plant will become the property of Haryana Agriculture University after 25 years of its operation and maintenance. The air quality at present is also getting worse, primarily because of some agricultural operations you see are like fires we produce here in Haryana, Punjab, a lot of this paddy crops, and the paddy straw is burned to cause the air pollution. I reside in Karnal, in the adjoining city of Panipat. The particulate material has increased by 4 times, some 386 microgram. This is more than normal. This is because of the burning of the crop residues. This is the report of 3rd of November. Another example of clean energy, can I say, is the wind turbines, which convert the kinetic energy in the wind into mechanical power. A generator can convert mechanical power into electricity. Mechanical power can also be utilized directly for specific tasks such as pumping of water. Wind power energy can be used in transportation and in food production. The benefits of wind power are renewable, benefits will be renewable energy, inexhaustible technology, not pollutant, clean fuel source, reduces the energy bills, cost effective, generation will create jobs. Wind turbines can be built on existing farms or pastures. It is sustainable and domestic source of energy. Wind power is cost effective as compared with conventional generation sources. Hydroelectricity is another example which can be produced from hydropower. In 2015, hydropower generated was about 16.6% of the total world electricity and 70% of the all renewable electricity. And this was expected to increase by about 3.1% each year for the next 25 years. The hydropower harnesses the power of water in motion, such as water flowing over a waterfall to generate electricity. A turbine converts the kinetic energy of falling water into mechanical energy. Then a generator can be placed in to use this conventional energy and generate a lot of energy for electrical energy purposes. The advantage of hydroelectricity are known for several years. In India also we have some hydropower generation plants, and this is a perhaps maybe we can give a new call that we should concentrate on hydropower electricity because it offers several advantages. It is reliable, it is adjustable, it creates lakes, it is very cost effective because some studies done in United States show that it takes only 0.85 cents per kilowatt per hour. And this is about 50% of the cost of nuclear energy, 40% of the cost of fossil fuel, and 25% of the cost of using natural gas. There are a large number of efforts that have been made in the use of these non-conventional sources of energy. And I hope there's a need for us to reinvent ourselves and the research programs. Also, the planners and professionals must take advantage of some of these new non-conventional sources of energy to ensure that we leave a very clean and neat environment for future generations. Thank you.
Thank you very much, sir, for your thought-provoking address. It has set a perfect platform for our speakers to deliver their presentations in the area of reducing carbon footprint in the dairy industry. Thank you so much, sir. Before calling our first speaker, I would like to inform all the participants that we would love to hear your queries during today's presentations. If you have a question for our speaker, please feel free to send it through the chat box. We will be answering questions at the end of the session. If we don't get to your question during today's webinar, we will be sure to follow up afterwards. Now, I would like to invite our first speaker, Dr. Sudhindra Tati. Dr. Sudhindra has a BTech from IIT Kharagpur and PhD in Material Science from University of Texas at Austin, and over 25 years experience in the semiconductor industry in the United States and Asia, covering new product development, quality, commercialization of new technologies, particularly for rural applications. He is in charge of innovation and facilitating collaboration with strategic partners. He started his career at Motorola Semiconductor and has since worked in semiconductor foundries in Thailand and Singapore. He was also involved with Amber Wave Systems, an MIT spin-off in Boston, pioneering the commercialization of strained silicon technology. His interests are in commercialization of new technologies for improving the lives of rural masses and in renewable energy. He is currently the CEO of Prompt Innovations. Sir, I invite you to deliver the lecture on the topic Sustainable Cooling Solution for Indian Dairy Industry, Milko Chill, an instant milk chiller at source. Over to you, sir.
Thank you. Thank you, Dr. Binu, for the introduction. Well, let me just share my presentation here.
Yes, sir.
Is it visible?
Yes, sir.
Thank you.
Yes, sir.
So thank you for the invitation and the opportunity to present here. Respected chief guest, faculty members, students, and fellow attendees. I'm representing Prompt Group today, which has been a technology solutions provider in the cow to consumer dairy supply chain for the past 3 decades. And it is my pleasure today to share with you an innovation that addresses some of the challenges of the Indian dairy industry. The motto at Prompt is pursuit of purity. And in that endeavor, we have developed a solution, and I'll be sharing a bit about it, particularly in the light of the sustainability, which is the topic for today, which is reducing the carbon footprint. So very basically, the carbon footprint definition is that it is a sum of all the greenhouse gases emitted through the life cycle of a product. For example, the carbon footprint generated by production of 1 liter milk. Now, there are about 17 goals that have been set up by the Sustainable Development Goals. This is a global UN effort. And interestingly, the experts have pointed out that in these 17 goals, something that was missed is the fact that sustainable cooling is also a very important aspect. Now, whether this is a blind spot or not, but today I will be covering one of the small but significant steps in dairy processing, which is the chilling of milk, which I believe is a significant step, but it also has a lot of opportunity for carbon footprint reduction. So let me start by talking about the context of the dairy industry. While we can certainly be very proud about our position as the largest milk producer, but we also face some challenges, and I think we can agree that there are a couple of areas of improvement. Number one, our industry loses substantial amount of milk due to spoilage. And secondly, we have a long way to go when it comes to quality, particularly when compared to global standards, when we measure it in terms of bacterial count. Now, fortunately, there is a growing awareness and motivation to improve the quality of milk. Now, to understand the quality of milk, I would like to draw your attention to this graph, which is a classic alpha Laval graph, which shows the growth of the bacteria with time. Now, the milk coming out of the udder of the cattle in India is as high a quality as anywhere in the world. So at time zero, we are equal. However, what happens is with time, the quality of milk begins to degrade, and that is due to bacteria. Now, if you pick one of the curves, let's pick up 25 degrees curve, you see that with time, there is an exponential growth of bacteria, which is what causes the degradation of milk. Now, a couple of things that are evident in this graph. One is that as you cool the milk temperature, then the bacterial growth is arrested, and hence it is good for the quality of milk. But second thing that is important here to notice is that not only the temperature, but when you chill it, for example, at what time after milking do you chill it, has a very significant impact on the quality of the milk. Now, ideally, the optimum point would be at source, that means immediately after milking. But in the Indian context, there are a couple of challenges. Number one, for us, source means small volumes produced by smallholder dairy farmers spread across very wide distances. Add to that the temperature, the harsh conditions of the climate, and also the lack of reliable electrical supply in rural villages. So it is clear that the current solutions of chilling are not adequate if we want to achieve global standards. And seen here in the red bar at the bottom is where the global standards are. We need to do a lot about it in order to improve the quality of milk. Now, with all these challenges in mind, we developed MilkoChill, which is an instant milk chiller with thermal storage. I'd like to draw your attention to the photograph on the left. The box number one is the cooling unit, which is what the heart of the system is. This is where the patented heat exchanger is, and the thermal storage also takes place here. The unit number two is the heat recovery unit. Now, this is the second patent, which is known as the multi-utility heat pump, where we are simultaneously generating two utilities at the same time. We are cooling milk on one hand, but we are also co-generating hot water on the other hand. I'll come to the benefits of this, but essentially these all result in energy efficiency and lower energy cost. The third is the refrigeration unit, which is of course used for the charging and refrigeration, and the control panel, which ties up all together and also measures, monitors, controls, and also displays some of the key performance parameters, such as the charging status or the outlet temperatures. Now, I mentioned to you about the rural infrastructure, and so two things I have to highlight about this product. One, that it works on single phase electricity. And secondly, we use a concept known as a thermal battery. So unlike an electrochemical battery, which is prone to maintenance and cost issues, the thermal battery is essentially a phase change material. When the electricity is available, it will charge up the cooling unit, store the energy, and hence at the time of chilling, which is in the morning and evening, even if there is no electricity, the chilling process will continue, hence reducing the dependence on a genset or any other expensive alternate power solution. The capacity of this unit is 500 liters, split into 250 liters in the morning and 250 liters in the evening. However, I must point out that you do not need to wait for the entire 250 liters to accumulate and then turn on the machine. As and when you get small volumes of milk, you start pouring into the machine, into the hopper at the top. For example, if a 40-liter can were to arrive, which would be at 37 degrees, you would pour it in the funnel here at the top, and milk would come down through the cooling unit and come out as cold milk, which can be collected in the can at the bottom in about 10 minutes. Now, this translates to 250 liters per hour of cooling rate, which is why this is known as an instant milk chiller. And it also, the average temperature of the entire batch of 250 liters of milk would be 7 degrees. Now, I must highlight the importance of the hot water. People in the dairy industry very well know that, as you do a chilling process, a CIP process, the clean in place process is an integral part of any operation. And so we not only recognize the importance of this, so we instituted a 3-step CIP process, but we also automated it to make it easier for the farmers. Now, this technology, this product was co-developed with technology licensing from IIT Bombay. And the combination of the patented thermodynamic design and the product design results in a truly differentiated product. Now, the technical features of instant chilling, the thermal bank, and the storage I already mentioned. The fact that the heat exchanger and the cold storage are combined into one box makes it a very compact machine. There are no moving parts, there are no pumps. Even the flow of milk is through gravity. All of this results in a very low energy consumption. The peak power requirement for this product is about a kilowatt. Now, there are serious implications of this, because now it not only results in huge energy savings, but it also allows us to integrate with other sources of renewable energy. So the combination of the heat recovery, the patented thermodynamic design, and all of this results in one of the most energy efficient machines in the capacity and the category of chilling. Now, we believe that this Milkochill has several potential places where it can be used. Now, whether it is in the cooperative sector or the private sector, the small milk collection centers spread across the country, many of them are in places where they may not have adequate rural chilling infrastructure. So these could be a nice collection point and a chilling point where the growth of the bacteria is arrested at an early stage, and then the milk can continue on its journey towards the chilling stations where the eventual chilling will take place. Now, individual farmers are also a potential customer here. Of the 96 million farmers spread across the country, most of them have 2 to 5 cattle, but even a small fraction of farmers who have milk collection of about 500 liters could benefit from the chilling at source, which would increase their shelf life and also increase their income. The unorganized sector also faces quite a bit of spoilage, and they could also benefit from this particular solution. Now, there are obviously economic benefits, because otherwise there would be no sense in producing a technology. So while there are benefits like reduced milk souring, better quality of milk, the product mix, higher milk price realization, and also wider sales outreach. The thing that I want to focus a little bit about how this is compares with the existing solutions and what more can be done to further reduce the energy. So let me first state that our value proposition is actually instant chilling. So there is no real comparison with a bulk milk cooler. However, bulk milk cooler is today the most entrenched and the existing solution. And so what we did was we wanted to compare the savings resulting from Milkochill by comparing a similar capacity. So in this case, a 500 liter capacity BMC with an air-cooled condenser. And we don't want to go into the numbers here, but with a combination of the lower energy consumption and the heat recovery, we end up with about 5 units per day of savings per machine. On the right-hand side of block, I have also mentioned about energy savings that result possibly due to lower pasteurization temperature. Now, it is known that the pasteurization temperature is a function of the bacterial loading. And so if the incoming quality would be better, as in lower bacterial count, it is quite possible that we would be able to lower the pasteurization temperature to 72, which is where it should be, rather than above 80 where it is currently being done. And hence that would be a further savings of about 300 units annually. Now if you total this up, then it results in more than 2,000 units per year of energy savings. Now if you take a CO2 emission factor, conversion factor of 0.83 kilograms per unit, this is a result of about 1.7 metric ton reduction in CO2. And if you multiply this by the total potential of all the possible chilling solutions out there, then it results in a significant volume of million metric tons, which is about 3.4 billion metric tons. Now, so far, so good. Now, this is what has already been executed. Now, the question is, what else can be done to reduce carbon footprint? And I'd like to propose 3 things. 2 of them are basically using it with renewable energy. And that is possible in our case, and possible only because of the low peak power design and the thermodynamic efficiency of the particular milk chiller. So first, let me talk about the setup that we have done for a modest size solar powered Milkochill. Now, one thing I want to highlight here for the benefit of all our friends is that we are big believers in distributed power generation as opposed to centralized power generation. So for each Milkochill machine, we could have its own solar power. And with a modest 3 kilowatt system, we could power up a Milkochill and be completely independent of the grid, savings in energy as well as in CO2. Now, there is only one challenge with solar, that the generation of solar is asynchronous with the use of the chilling process, because chilling happens in the early morning and late evening, whereas generation happens during the day. Hence, we have to resort to some sort of an energy storage here. And so there is still a lot of room for innovation in the area of storage as well as the solar efficiencies. But the combination of solar and a Milkochill would result in quite a bit of economic benefit as well as CO2 reduction. And this is a schematic of how multiple milk collection centers could have one and then could be collected, and then cold milk could be taken directly to the production unit. The savings that were there in the through the grid, which are now converted by, which are powered now by solar, would now amplify our CO2 emission reduction from 3.8 million tons to about 10.8 million tons. Now, the next logical question, natural question, is we have farm, we have cattle, and so we have cow dung. So how about biogas? And that's a very natural question. And we tried initially with a balloon type of a digester, because remember, we are still talking about distributed power, and with a 10-meter cube type of a balloon digester powering up a biogas genset, it would be great if you could operate the instant chiller, and simultaneously we are generating the slurry, which has huge not only fertilizer benefits but also quite a bit of economic benefits. Now, I understand that in the edition 1 of the session, and also Professor Rajoria just mentioned in his keynote about the importance of biogas, and we can corroborate and we can absolutely agree that biogas is a great potent combination to power up sources. And in addition to the economic or the energy benefits that I mentioned, just like solar, there are some serious additional benefits such as free cooking gas. There is manure management. Now, the hygiene conditions are significantly improved when you take heaps of cow dung which are lying unutilized, and we are converting it into a good energy source. And additional income also through carbon credit or slurry and through manure. Now, we have seen some great examples executed by some environmental agencies which are spread across districts and states. And we have seen operational biogas units for more than 12, 13 years. And the main reason for the success is simply the incentive of carbon credit. So one point I would like to make for my dear friends is, no matter how good a technology is, unless there are some incentives or economic benefits for the farmers, it will be very difficult for them to embrace. And so whatever we do, we have to keep in mind the incentive portion or the economic benefit portion. And biogas happens to be one of them where it could really add to that incentive. The third thing we could do is obviously move to natural refrigerants as a long-term solution. Today, we are using the standard refrigerant, which has an ozone depleting potential. But as you can see, there are a number of gases with a GWP and ODP potentials, which are quite low. And so we can leapfrog from where we are today and move towards naturally occurring natural refrigerants as a long term. Now, what I have mentioned to you is only one portion of the entire cow to consumer supply chain. So in this organized sector, as you can see, from cattle to consumer, you go through several steps. And the instant milk chiller is something, whether it is at source or at a milk collection center. However, taking a very broader look, there is a need for a sustainable cold chain, the entire chain being cold. And hence, there is a lot of innovations that are required, both on materials as well as processes, in terms of reefer transports, cold transports, or even in the processing plants at the dairies. So I think there is a challenge here that we need to accept, that there are a lot of potential opportunities to innovate, and we as technologists and scientists, we need to come up and face this challenge and offer our solutions. Now, in the recent presentations by the Department of Animal Husbandry, a couple of things have been pointed out. First is that there is an infrastructure gap of about 125 million metric tons, and that enhanced chilling infrastructure is one of the 5 significant areas of investment. What it means is that what we have in chilling infrastructure is not adequate even today, and at the growth rate considered, gap is going to get wider. So yes, we do need to increase our chilling capacities. We do need to do more chilling. We don't have any other alternative but to use colder temperatures. The key question that we need to ask as developers of technology is, can we achieve a balance? Can we solve both the challenge of ensuring the need for cooling on one hand, and can we simultaneously mitigate the energy and the environmental impacts? So in conclusion, I would like to submit that Milkochill, the instant milk chiller, is an innovative, viable, Atmanirbhar, and sustainable complementary alternative to existing solutions it fits very nicely into the supply chain. Milk-Ochil is a win-win for both farmers as well as the dairy. We look forward to the day when farmers are paid not only for fat and SNF as they are today, but maybe even highly incentivized for high quality, as in lower bacterial count. We look forward to the day when India is known not just as number one in quantity, but also in quality. Now, while retaining milk quality is the primary goal, Milk-Ochil can also make a huge socio-economic and an environmental impact through increased farmers' income and reduced carbon footprint. So I thank you for giving me the opportunity to share with you a very simple but significant contribution to the dairy industry. Thank you.
Thank you, sir. Thank you for giving a very practical and valuable insight. Thanks once again, sir. I'm glad to inform you that the next presentation will be made by Professor Mani Shankar Das Gupta. Dr. Das Gupta has 27 years of teaching and research experience at BITS Pilani, India in Mechanical Engineering Department. He has been part and parcel of several initiatives scripting the phenomenal growth story of BITS Pilani as an institute of eminence as announced by the Government of India in 2018. He has mentored and motivated several students who subsequently grew to be among the high achievers across the globe, both in corporate and in research. Dr. Das Gupta mentored several innovative initiatives by students. Well known among them are initiatives like Rural Transport Vehicle Design suitable for negotiating road with RUTS Hyperloop India, contesting at SpaceX Hyperloop Pod competition at Texas A&M University, and California reconfigurable VTOL Garud design for the Vertical Flight Society contest at USA. Dr. Das Gupta has primary research interest in environmental friendly technologies, especially in carbon dioxide transcritical systems for HVAC application. Dr. Das Gupta is recipient of several awards, including Young Scientist Award from Department of Science and Technology, New Delhi. He served as the Chief of Placement Unit of BITS Pilani University, spread across 3 campuses within India for 12 years. He also served as head of the department at the main campus of BITS Pilani in 2 stints for a total duration of about 5 years. So without taking much time, I would like to invite Dr. Das Gupta to deliver the lecture on a topic very close to his heart, and that is carbon dioxide heat pump for waste heat recovery and utilization in dairy industry. Over to you, sir.
Yeah, I hope I'm audible. Welcome,
Yes,
all of you. It's my pleasure to be invited to speak in this webinar, and I'd like to express my sincere thanks and respect to all the august audience here. I will also be using some PowerPoint, so let me share my PowerPoint. So I hope it is visible. I'm not, okay, I can go to the
Yes, sir.
presentation mode. Yeah.
Yes, sir.
So the theme of this webinar is reduction of carbon footprint in dairy industry, future and challenges, edition number 2. I'm really glad to be associated with the edition number 2. And I would like to be in touch with any future development in this area because one of my research areas really well connected with this. So I belong to Mechanical Engineering Department, BITS Pilani. It was established, the Mechanical Engineering Department is established in 1946. It offers BE in Mechanical Engineering and Manufacturing and Master Degree in Design, Manufacturing.
Sorry to interrupt you, sir.
As well as PhD program.
Sorry,
So,
sir. Sir,
yes.
If I may request you to please kindly present the presentation again.
Sure. Is it gone? Sorry. Okay, just a minute. I'll have to
Yes, sir.
open it. Yeah, I hope it is visible.
Yes, sir.
Okay, thank you. So I just started with introducing the department, which is established in 1946 at BITS Pilani, and it is focused to BE program, master's program, as well as PhD. So
Sir, I
my
request
topic.
you to, sir, kindly slideshow into the profiles.
Okay.
Yes, sir.
Sure.
Thank
So
you,
this, yeah. So this topic today for my presentation or discussion will be CO2 heat pump for waste heat recovery and utilization. It is based on some publication which was presented at Purdue University in 2016 by one of my research scholar, Dr. Simarpreet. I am Professor M.S. Dashgupta, currently HOD of Mechanical Engineering, and I have also put my email ID, official email ID. Please feel free to connect with me if you have any query further. Because today's presentation, I will not go into much of the technical detail, but we'll look at the results and then application area. And I also do look forward to collaboration, because I understand a lot of viewers in this session are connected with the research and teaching in the dairy farm, and I do have certain interest in this area where collaboration is very much possible. So milk as a food, we can view it as a resource, great resource for India. It is extremely important resource to ensure food security and nutrition for a very large population in the country. There is refrigeration needs at various stages in milk production, as it is highly perishable, as also pointed out by the previous speaker. It has heating and cooling needs both. It is had substantial export potential and scope of growth. For example, some statistics is given in the last bullet. And further, it has got tremendous opportunity for entrepreneurship for the young students and researchers who are working in this area, dairy farm area. There is definitely tremendous opportunity for entrepreneurship in this area. If we look at the global growth rate in dairy industry, it is phenomenal, and it is much more prominent in countries in Asia, and India contributes to a great extent in this. European and other countries, the technology might have been saturated mostly, so the growth is at present not seen as vast as in case of in Asian countries. Okay? In terms of the milk consumption in India, compared to 1950s and compared to 2020, it is a many-fold increase. And that has been possible due to technology intervention and, of course, growth in the dairy industry. So there is need of technology intervention in this. If we look at the energy demand, there is huge energy demand in the dairy industry, both for heating, for cooling, for transport, and for storage. So the major points, if we list out, are in terms of steam for heating, because most of the plants in India still uses coal-fired system. We also use high-speed diesel, HSD, which is the second one. We also use electricity. The use of electricity is increasing day by day. And of course, there are others. Sorry. So we made our study in a location. We made our study at a location in Punjab. interruption. So we, which is the milk storage plant and data, energy uses. So if we look at this plant, it was something like this. It receives milk, okay, and then it is stored at about 5 degrees centigrade. It is pasteurized, and then we have separation process, and then certain milk-derived products are made, which include butter, clarified milk, condensed milk, etc., etc. And there are some processes and some products. So that's the, in total, the footprint of that industry that we are talking about. The plant description, that is in terms of the energy uses, we can look at the evaporative condenser side, so which is basically using groundwater, and so cooling water is used, which is fresh water from ground, and then a fan is used, and then we have ammonia-based chilling plant. That's what is also mostly used in most part of our country. We have a boiler which is receiving heat from a plant which is coal-fired, and we have the boiler supports pasteurization, milk heating and processing, and then CIP activities. So the boiler exhaust is used in auxiliary air heating unit. After that, the boiler exhaust from the passes to a dust collector. It passes to a water heating unit, and then after passing through a scrubber, it is exhausted through the chimney. So we studied this plant, its year-round operation, energy footprint, etc., etc., and then we plotted all those things. There are few things which are observed is that the plant uses a very low grade coal, which is having a calorific value of about 3,500 calorific value, which is also later on we found out that it is more or less common for most of other milk processing plants in northern part of the India. Also, there are huge difference in the amount of milk received in various months. So this chart on your screen discusses that, which also discusses the variation of ambient temperature in that location in Punjab. It is based in Amritsar, nearby Amritsar actually. And there is difference in receipt of amount of milk and energy footprint. So all these things we studied and then came up with certain plan, which is to use a CO2 based heat pump. So this region which is marked out by a red circle is our introduction, where we have introduced a heat pump. What it does, the groundwater is heated, WPH unit, as we can see, is heated in this unit, and then before going into the boiler, it is further heated by the heat which is exhausted from the condenser of the NS3 unit. So this is used as a evaporator that side for the CO2 unit, and then as a gas cooler, which transfers the heat to the water. And this unit, using CO2 as a fluid, was found to be very, very effective. We got good results in case of cooling operation, as well as in case of heating operation at various temperature range, that is ambient temperature range. And this is the result which we published later. So if we go into the overall, so approximately 37 kilowatt per hour of heat is recovered, which was otherwise rejected to the atmosphere. So we also reduce the water uses from groundwater for cooling, which is saved. Total electricity consumption, of course, increased in this operation because we had to run an additional compressor there. Overall coal consumption is reduced drastically. CO2 emission is reduced, and overall energy cost is also reduced. We also did some preliminary cost analysis, and we found that the additional cost can be recovered in about 18 months of operation. So if we look at the overall impact of this exercise, so we have electricity consumption, which increased by about 38%, of course. However, the water consumption, fresh groundwater consumption reduced drastically. We have reduced the coal consumption by 48% and the CO2 emission by about 47.7%, and total energy cost in terms of balancing the electricity consumption and coal cost, etc., we saved about 43.1%. So this is one exercise which we have done and then have some results to show. Overall, the milk transport also uses a lot of energy. Our previous speaker basically devoted to that particular one. So in India, we have iced transport in insulated trucks for small haul and standard refuse transport when the product is value added, for example, Amul butter or things like that. Okay. Otherwise, within the small short distance transport, we generally don't use any refrigerated transport. So that, of course, reduces the quality of the product. That's something we have to be careful about it. So overall in India, this is not, of course, a statistics of only of the milk or dairy industry. About 104 million metric ton of perishable product is transported per year between cities in India. Of this figure, about 100 million metric ton moves by non-refer mode, that is non-refrigerated mode, while only 4 metric ton moves by this, which is of course 2013 data. That's what we could immediately get, but the figure is not very encouraging even today. Even on the front, when we uses refrigerated transport, proper refrigerated transport, we generally still use R22, which has been banned in many of the European countries, and R404A, which are generally used in India. Retrofittable alternatives are there, of course. Nowadays, retrofittable in the sense you don't need to make a lot of changes, technical changes or changes of component in the refrigeration circuitry, but directly use R407A by F, which is being implemented. However, on focus is low charge ammonia system for refrigerated transport, which is one, and of course use any other natural refrigerant, for example, CO2. Okay, there is a lot of debate and a lot of choice to be made between equipment versus choice of refrigerant also. If we look at this, the environmental implication of the choice of new equipment and choice of new refrigerants are likely to be increasingly open to review. As you replace your old and aging machinery, many things will improve. The technologies are improving in terms of refrigeration. The leakage of refrigerant will reduce, right? And newer refrigeration units will be using some of the fluids, refrigerants or fluids, which are more environmentally compliant, but then there are other costs associated with it. Okay, particularly with respect to GHG emission associated with the sourcing and use location, because some of these new technologies, again, you may have to bring the whole unit, carry or transport the whole unit from US or UK or any other countries, and then there are associated GHG emission there during the transport itself. So there are controversy about that also. India, as a member of the Group 2 countries, as per the Kigali Amendment, as you know, have a longer time frame for reducing the use of HFCs in refrigeration uses compared to European countries, which are signatory of the Group 1. So there is a chance that we can wait for more time, let the Western countries adopt something, get it tested, proven, and then import that technology and install it here. But then, of course, at the cost of innovation, because once those technologies are established, you are basically purchasing them and putting for your use, and you are losing the innovation component, and then you are paying money for that. So there is tremendous need that we invest in technologies and invest in research in this area. So if we look at alternatives for milk chilling or milk refrigeration plants, most of these plants in India are ammonia based, NH3 based. And it is actually not very easy to find a replacement for NH3 because NH3 has got certain advantages. Of course, it is has disadvantages. For example, if moisture goes in, that properties degrade fast. It is bulky. It is, if there is leakage, then it is toxic, and so on. But then it has got huge advantage in terms of the working because it maintains a high COP. NH3 plants maintains a high COP at high temperature or high ambient of Indian condition. Okay. So an energy efficient operation of any of the vapor compression cycle we are talking about not only help to save electricity bill, but today it is also being increasingly associated with saving fossil fuel, that is secondary emission, and reduction of overall carbon footprint. Some of the well-recognized strategies to improve the energy efficiency of refrigerants, for example, from the UN report we can pick up, number one is minimizing the cooling load with various other methods, minimizing the temperature lift, accounting for the variable operating condition, temperature lift in terms of increasing the efficiency of the heat exchanger so that the approach temperature or delta T that you need to reject heat to the atmosphere can be reduced using better material, better heat exchanger design, compact heat exchanger design, etc. And accounting for variable operating condition, because in India, most of the cities, the temperature variation may be really very large. So the refrigeration systems basically land up operating in a non-optimum condition for a large amount of time within the year. That we have seen for the unit in the Punjab, because there is huge difference between the winter and the summer temperature. Selecting the most efficient refrigeration cycle and component, because in this area, although it may appear very simple, but then not much work has been done. Many of the refrigeration units are a copy of designs which had been working elsewhere in other countries, and we have great potential to redesign that for Indian atmospheric condition. A design of effective control system for various specific application, because if it is for milk chilling application, we need to design that refrigeration system exactly for that, okay? Because there is specific need there. Checking operative performance and correcting the faults, etc. There are some India-specific challenges also of refrigeration system, be it in milk plant, dairy processing plant, or any other unit that we may apply them. The refrigeration system used in very hot ambient generally uses more energy than equivalent system in cooler countries, because the number one, very obvious, the cooling load is higher for a given mass of load, because the incoming material is at 35 degrees, 40 degrees sometimes in the summer, and so on. The temperature lift is bigger in the heat rejection end, because the hot end of the plant need to reject heat at much higher ambient temperature, which may be at 45 degrees. So you need to push up the temperature to 50 degrees to have a delta T to reject the heat. So 1 degree centigrade temperature lift adds about 2 to 4% in the energy demand in the plant, and that therefore the efficiency or the working of refrigeration plants which are used in dairy industry or any other industry in India cannot be compared vis-a-vis a similar plant used elsewhere, and plants need to be designed for specific purposes. India has fulfilled the Montreal Protocol targets much ahead of the time, is one of the countries which has fulfilled it much ahead of the time, and it should aspire to maintain that legacy in terms of Kigali Amendment also. So this is my submission, and that entails that a lot of research should be done and should be focused on this area. CO2 is coming up as a big alternative as a refrigerant because it has got global warming potential as one, or that is the reference basically, and there is no potential for ozone gas depletion. Plus it is a biosphere gas, so we live in harmony with CO2 around air, and then it is not affecting our environment anyway. Okay, of course, concentration of CO2 at one place can be harmful sometimes, but that's not a very big danger. It is not poisonous as such. Okay. And this, there is advantage of CO2 as a refrigerant, liquid CO2 as a refrigerant when you use at a temperature that is below or around minus 40 degrees centigrade, which is used for long-term storage of dairy product, which is property, or there is thermophysical properties of CO2 is much better compared to NH3. I have put some comparative data, and this is the place where we can use CO2. So a alternative can be, in case of the NH3 or ammonia being used in a lot of the refrigeration plant, an alternative can be to use a cascaded system in which lower temperature is covered by CO2, higher temperature by NH3. So that will do few things. It will improve the COP of the system. It will not come in contact with food material, NH3. It will also make the ammonia charge lesser, because in some of the states and some of the most populated areas, there is restriction of putting up ammonia plant because of its toxicity. However, when the charge can be reduced in the ammonia plant, we can use such plant near the cities and other places. Thanks all of you. I welcome questions and queries. I have avoided some of the technical details in the work and put up more on in terms of discussion, in terms of results. However, we can discuss, and then I'm open to collaboration in this area or any other with faculty members, researchers in this area. Thank you. Thank you all.
Thank you so much, sir, for giving your valuable insights in the area of waste heat recovery and utilization in dairy industry. So thank you once again. So if there are any queries which we will receive in the chat box, we will communicate with you at the end of the seminar or even afterwards if we get any queries from the all the participants. Thank you, sir.
Sure. Thank you.
Now, I would like to invite our third speaker, Mr. Priyank Mehta. Mr. Priyank Mehta has done BTech from Nirma University and MTech from IIT Gandhinagar in Mechanical Engineering. He started his career at Banas Dairy in 2018. He is in charge of workshop department where he is looking at the maintenance of ghee section, paneer section, dahi section, milk processing, as well as the operation of 11 kV substation and refrigeration plant. He is also involved in the project work of cold store with refrigeration and the biogas plant. Sir, I invite you to deliver the lecture on Banas Bio-CNG plant. Over to you, sir.
Thank you. Thank you for the introduction. I am going to the slide. I hope slide is visible.
Yes, sir.
Okay. First of all, good afternoon and namaste to all. It is first. I would like to congratulate whole MIDFT team for a good initiative of this webinar that is on reducing carbon footprint in dairy industries, future and challenges. This is important and crucial topic because it is in front of us, but we are unable to see it. So this is great initiatives. So come to my topic, that is Banas Bio-CNG plant or Banas biogas plant. In my presentation, I briefly introduce about Banas Dairy and its initiatives, then introduction to biogas plant, then key favorable factors that help us while setting our biogas plant, then advantages of a biogas plant, then specifically about our Dama biogas project, then project costing and payback period. So, may you all aware about Banas Dairy, a part of Amul, who established in 1969, currently operation in Gujarat, Rajasthan, and 28 districts of Uttar Pradesh. And as of date, it is Asia's largest cooperative dairy. May you all aware about the vision of our Honorable Prime Minister that doubling the farmer income by 2022. So with the same aim, Banas Dairy took many initiatives other than milk and milk products, which includes value addition in potato products. We also started honeybee rearing, collection, processing and packaging. We also started edible oil packaging facility. With the government of Gujarat, we also take initiation of take-home ration at our Badarpura plant. We are the first dairy who's having a medical college, which is located in Palanpur. And we have set ambitious target to plant 10 crore trees in 10 years. And in last 2 years, we have already planted more than 1.5 crore trees within our districts. In addition to these all initiatives, we also took initiatives of a multi-beneficiary biogas project, which we already started in our Dama cement station, and gas of the production is already started. In upcoming, we have planned to set up at least 50 such plants within a district of Banaskata, at least 50 such plants within a district of Banaskata. If I talk about the main objectives, of course, the additional income to the farmer, convert waste to wealth, improve hygiene and environmental condition, provide nutrient-rich fertilizer, provide clean energy, and also generate employment within that near villages. If I talk about the key favorable factors that help us while setting our plant, so first, most important, the availability of raw material, which for our plant, we have used cow dung and rotten potato as a raw material. We have more than 1.7 million cattle in our region, so there is a huge amount of cow dung available for us, as well as Banaskata is also one of the major potato processing district in our country. So there, if I take an example of a DISA who having more than 220 cold storage, which is located to our Dama site. While screening the potatoes, there are many amount of rotten potatoes are there, which is a problem for the cold store for the disposal. So we can easily utilize in our biogas plant. Other than that, there is a requirement to increase the farmer income. There is a requirement to replacement of a fossil fuel. There is a requirement to improve the rural hygiene, also to promote organic farming, also to provide nutrient-rich fertilizer so that chemical fertilizer can be avoided, as well as the best thing about our plant of the site location, as it is on highway, so vehicle operating on CNGs are easily available, so generating biogas, converting into bio-CNG can easily be utilized. So if I talk about the advantages, this is just an example. If a farmer is having 5 cows, on an average 15 kg of a dung is produced from a single cow, and we are purchasing cow dung at a rupees of 1 rupees for 1 kg of cow dung. So approximately 75 rupees will be the additional income per day, and if we annually you can say that almost 27,000, more than 27,000 we are paying to the farmers. Other than that, there is a common practice that cow dung is keep at the corner of its farm or near to the animal. So if they are selling it to the biogas plant, then the land occupied by that cow dung can be utilized for other purposes. Other than that, it will be reduce the labor requirement for the handling of that dung. This will also improve the hygiene condition of that farm and village. It definitely improve the health of animal and that farm. The biogas plant also help to provide a very nutrient-rich and nutrient-rich fertilizer and manure. Also, it will reduce the it will provide a substitute for a fossil fuel, clean energy that is bio-CNG. Other than that, environmental factor, it will also protect our environment as it will significantly lower the greenhouse effect. If we can here also, it will help to reduce 2 critical important greenhouse gases that are methane and carbon dioxide. If we quantify it, so our plant capacity is, can generate 800 kgs of bio-CNG, which is equivalent to 20 tons of CO2 per day. So we can able to capture this amount of CO2 with the help of our biogas. In addition to that, if we are using that bio-CNG in a place of a petrol, then also we are able to save emission of 2.8 tons of carbon dioxide. This will be corresponding to our production. Now, specifically about our biogas plant, we have our biogas plant of a capacity of 2000 cubic meter per day. After purifying it, we will having 800 kgs of a bio-CNG. For that plant, we require 40 tons of a cow dung, which we are procuring from nearby villages. In our like we have covered almost 12 villages to that site. From that, we are contacting with 254 farmers which are already connected with us. If I talk about the components, so here are the components. That is, cow dung collection is a procedure, weighbridge, unloading tank, mixing tank, digester, gas balloon, purification system, compression process, cascade system, dispenser, solid liquid separator, vermicompost, and liquid fertilizer tank. I will explain briefly about these all process components. First, the cow dung collection. We have made a very systematic way in which a tractor with trolley with weighbridge going to the farmer house and collecting a dung and informing the amount of dung that how much they are collected. In addition to that, we are also developing a mobile application similar to the milk. The cow dung procurement will be directly informed to the farmer. As we are paying 1 rupees for a 1 rupees for a kg of a cow dung, the payment of the farmer will be paid to the farmer with the milk payment into directly their account on every 15 days.
Yes, sorry for interruption. Sorry for interruption. Can you please present the presentation again?
Okay.
Yes, sir.
Like from the starting?
Yeah, no, sir. Just from this slide onwards.
From this slide onwards. Okay.
Yes, sir.
From this slide or? Okay. So after collecting a cow dung from villages, the tractor and trolley comes to our plant, biogas plant itself.
Sorry, sir. Sir, it's not visible. Can you please present it again?
Share.
Yes, sir.
Share again.
So first we have to stop the presentation and
then share
after
again.
Sorry?
First we have to stop the presentation. Then after present now, freshly you click on the present now.
Okay. Now is it visible?
No, sir.
No, it is not visible.
Yes, sir. The slide show.
Okay, so now it is visible.
Yes, sir. Yes, sir.
Okay.
Thank you.
We have developed a very systematic way of collecting a cow dung. A tractor with trolley moves to the farmer house and collecting a cow dung from them. The weight of a cow dung is weighted at a farmer place, and we are informing to the farmer the amount of a cow dung we have purchased from them. We are also developing a mobile application so that they directly inform through a message about the cow dung what we have purchased. As we are paying 1 rupees for a cow dung, so the total payment of the cow dung will be are paying to the farmer with the milk payment on every 15 days. After collecting from a farmer place, it is transferred to our biogas plant where quality of cow dung is checked, with the visually checked, and the total weight of a dung is checked. After that, it is moved to unloading tank where use tractor hydraulic directly dump into our unloading tank where we are mixing with the water in a 1:1 ratio. For example, 40 tons of cow dung require 40,000 liters of water. We are mixing it with the agitators. After that, we are transferring the slurry into the digester, where in absence of oxygen, biogas production will take place. We have a digester having a capacity of 30 lakhs liter. The retention time of the slurry is around 35 days. After digester, we have two streams like gas stream and slurry stream. So I will explain first about the gas stream. So the produced gas is collected in our balloons. In our plant, we have two balloons having capacity 1000 and 500. The raw biogas is firstly collected and stored in this balloon. After that, it passed through the purification system where methane enrichment process will take place. In a raw biogas, on an average, the methane percent is around 55 to 65, carbon dioxide is around 30 to 35, and traces of H2S and moisture is there. So after purification, we are getting around more than 94, 95, 96% of purified methane, which we are going to compress. As after outlet of a purification system, the pressure is around 0.3 bar. So to utilize in a vehicle, we have to compress it. For that, we are using a compressor from 0.3 to 200 bar. Before selling it to the customer into vehicle, filling into the vehicle, we are storing the purified gas in a casket. We having approximately 2 days storage at our site. Of this casket, we are selling it through our dispenser, where vehicles with CNG cylinder come to our site, like similar to selling of a CNG, bio CNG as sell. You can see here the comparison of CNG and purified bio CNG. So you can see methane percentage, on an average we having a 95 percentage. So methane is more, corresponding to the calorific value is also more, which will help. We also actually get a feedback from a many customer that the average of a vehicle increase. So because of this calorific value. The other stream is the slurry part. So the slurry overflow of a digester, we pass it through the solid liquid separator. The solid part and liquid part get separated through this. The solid part is further treated for value addition, like we are making it vermicompost and a prom from this fertilizer. After value addition, we are packing and selling back to the farmer so that it will be a good fertilizer for them. The liquid part, we have actually collected enough tank and transfer it to the farmer or selling to the farmer through a tanker. It will help actually, it help to retain the moisture content of a soil, and the yield of the land also increases with this fertilizer. Now about the project costing. So approximately we have invested 8 crore rupees for our plant. If I talk about the OPEX, so we have considered, like you can see here, we have considered cow dung, like the raw material, transportation, electricity, manpower, interest and depreciation. For a year, it's come out to be almost 4.6 crore. Now if I talk about the revenue, so for our product, we have bio CNG, solid fertilizer, liquid fertilizer and vermi wash. A vermi wash will be generated due to when we created the vermi compost. So this will equal to our approx gives us around 6 crore rupees yearly. And there is an option of a subsidy for this around 2000 cubic meter of gas. There is a chance of a 66 lakhs of rupees. We actually already apply for a subsidy. Still we are in the process. If I talk about the payback period, so almost you can consider the total revenue of 6 crore. Total investment is for like operation cost 4.6 crore. Net profit and payback period will be around 5.4 years. So this is for a renewable energy. This is a good payback period. Now I would like to show you a small video of a 1 minute of our plant. I hope it is visible.
Yes, sir.
Thank you. Thank you from my side.
Thank you, sir, for giving a comprehensive overview of the biogas CNG plant at Banas. Thank you once again, sir. I'm glad to inform you all that the next presentation on the topic energy conservation in dairy industry will be made by Dr. J.V. Parekh. Dr. J.V. Parekh, since 1980, he is working as technical consultant for dairy and food industries and has provided technical and turnkey consultancy to numerous companies in the field of dairy and food processing. Dr. J.V. Parekh has written a book on technology of dairy products and has contributed many scientific and technical articles in Indian and international technical journals and also presented many technical papers in national and international symposia. He is life member of Indian Dairy Association and Association of Food Scientists and Technologists of India. Dr. Parekh has received numerous awards, but to name a few, recently on 2nd March 2013, he has been awarded with Dr. J.R. Patel Memorial Award for Dairy Professional for his outstanding contribution to the development and growth of the dairy industry. Dr. Parekh is a CEC member of Indian Dairy Association, New Delhi, and is chief editor of Dairy Times. So without taking much time, I would now like to call upon Dr. J.V. Parekh, sir, to kindly deliver the presentation. Over to you, sir.
Good afternoon to all of you. Can you hear me, please?
Yes, sir, we can hear you.
Yeah. Many thanks for nice words. I would also like to thank Dr. P.R. Patel and Dr. Shukla for inviting me on this prestigious webinar on energy conservations. Well, I think we had a very good learned speakers. I am the last speaker. Hope that everybody will hear me. Well, I will be just reviewing whatever the energy conservation is happening in the dairy industry. I have got some PPT presentations, so I request my secretary to have a presentation, please. Arpita, can you hear me?
The presentation is online, Dr. Parekh. You can continue.
Yeah, but I want to have some PPT presentation, which will make a little bit my job easy.
Your presentation
The
is
PPT is
on.
on the.
I could not see the slides on my. It's not visible to me. Or Dr. Goel can also help me because I have already sent some of the presentations.
Yes, sir. Yes, sir. We will now present the
That will be more easy.
Can you see? Can you see the presentation now?
No.
Sir, I'm presenting it from here.
Yeah, that would be better.
Yes, sir. So is it visible now to you?
No.
Sir, is it visible now?
Yeah, it is visible now.
Yes, sir.
Yeah, so just I want to review, as I mentioned to you, about what are the energy conservation taking places in different options of the in our dairy plants. Just I have given you some of the summaries of the what are the various services required in the dairy plant. For the liquid milk, maybe 0.8 to 1 liter, maybe water may be required per liter of the milk. Maybe the product factory, maybe little bit more water will be required. Power also, I think 1 kilowatt will process about 40 liters of the milk, and in the LDO and other furnace oil, it will process about 35 to 40 liters, 400 liters of the milk. And in the steam required will be about, 8 to 10 liters milk will require about 1 kg of the steam of the low pressure steams. In the refrigeration plant also I mentioned that about 1000 to 1200 liters of the milk. For that we require about 1 tons of the refrigerant. And the product factory liquid milk, the liters will go down, maybe 600 to 800 liters. So these are some of the basic services which we use in the dairy plants. Can I next slide, please? Now mainly I'll be talking about the upgradation of the 3 services which can be considered. First is the utilities consumptions, second will be the processing and product manufacturing, and third is the milk packaging. Next slide, please. Yeah, you see that here also in utilities, mainly it will be the electricity, refrigeration, steam, water, and the compressor. These are the main utilities required in the dairy plants. Yes, please. Next. Electrical energy, following are some of the technical upgradation which can contribute to the reduction in the electric energy consumptions. I have given some of the examples. Next slide, please. See, generally, when we are talking about the electric power requirements, we are talking about the mainly electric motors. So you'll find that if we are using the high efficiency motors, there could be a saving of the power maybe up to the 3% compared to any other standard motors. So these motors can offer a quicker and the cooler operation, high reliability and a longer shelf life, increase the profit from a lower operating cost. I have shown some 15 kilowatt motors. What are the economics is happening when you are using the high efficiency motors. Next, please. See, you can see here that how much if you are using energy efficient motor compared to standard motors, lot of saving is there. Some of the cost of the kilowatt I little bit taken lower, which is a little bit old data. But if you can see that payback period is also becoming 2.5 months, and the recovery of the one-time cost comes in 1.3 years. So when you are using the most efficient motor, energy efficient motor, that saves a lot of your power and it can economize. Next, please. Also, we are using a lot of VFD also, and sometimes we are using the throttling valves. So these throttling valves has a little bit problems as compared to our variable frequency drives, which can be in conjunction with the pressure, and the flow measuring device can be automatically vary the speed of the pumps or fans and compressors to suit the actual load requirements. These are much more economical than the throttling valves to regulate the flow. The energy saving of potential of 30 kilowatt variable VFD also I have shown in my next slide. Next slide, please. So here you can see that on the left hand side, when you are having to do the throttling, reducing the plant capacity or the pump capacity from 90% to the down, you can see the lot of energy saving is there compared to our throttling valves. So we recommend that we should use the more VFD type of the operations, which can be easily operated. You can see on the right hand side, last column, lot of saving is there in terms of rupees also. So when you are using that type VFD, it has got a lot of other advantages when you want to control the flow. So we recommend that we should have a sort of a VFD type of the operations, which can be connected with the online compared to the throttling ones. Next, please. Now, building automation is also very much important, as particularly controlling of the building services such as air conditioning, hot water generation, lighting, mechanical plants, monitoring and alarm system, as well as in the centralized security. So if you have got some building automation in the dairy plant also, they should also save at different levels lots of energy. Next, please. Now we are talking about the refrigeration, so which is consumes over 50% of the electricity energy of the typical dairy plant. Some of the technical development in refrigeration equipment which can help to reducing the energy consumption are as under. Next, please. So here I am talking about these screw compressors, which is very much important in our refrigeration plant as compared to the reciprocating compressors. If you use these compressors, which will have better, it will give high coefficient of the performance, COP, and lesser power consumption. So this will have a lot of advantages, other also, like a step-less capacity control to ensure the accurate temperature pressure control and thereby saving the energy. Higher reliability with the minimum maintenance requirement and longer shelf life. So we suggest that we should use this screw compressor as compared to the reciprocating type of the compressor in the dairy plant. Next, please. Same, I am just talking about the PHE type of the condensers, which are presently available, which are very compact in design due to the higher heat transfer coefficient and consume less power and water. The capital cost of the PHE type is also lower than the atmospheric type of the condenser. I have also shown some comparison in the next slide. Can I have next slide? Here you can see the lot of saving is there when you are using PHE type of the condenser as compared to the atmospheric type. At the last you can see the total PHE type requirement HP is 17.5 and then atmospheric requirement is 20. So you can see we should propose that we should use a PHE type of the condensers rather than the atmospheric type of the condensers. Next, please. Now, in the IBT system also, generally we conventional type, you don't use this PHE type of the pre-chillers, which is also very useful when there is a chilled water is retaining from the process. If you put the pre-chiller and cool down the temperature of the chilled water to 2 degrees centigrade before entering IBT, due to the high heat transfer and coefficient provided by the PHE, the requirement of ice bank coil length comes down, which results into a smaller IBT size and lesser capital cost as compared to the conventional system of the same capacity. So I would suggest that we should use PHE type of the pre-chiller system in the IBT systems. Next, please. So I have shown the diagram also where you can see that on the left on the top there is the IBT system, then our working pump is there, then a process PHE is there. From there it is going directly to the pre-chiller and then it goes to the IBT. So chilled water is cooled down in the pre-chiller 2 degrees and then it goes to the IBT. So in that way size of the IBT can be reduced and efficiency can be created. Next, please. Now this is what I have tried to show, that how much consumptions of the PHE type of the chiller helps when you got section temperature -2. If you see on the right side, increase in the COP is 27.1%. So the same other parameters are also there. So there is a lot of advantages when you are using the PHE type of the pre-chiller. The load will go down and also the COP of the machine compressor will be improved on a lot. Next, please. We are also recommending that air cooling units with the SS tubes. Air cooling units with the SS tubes and the aluminum fans are available presently. They offer following advantage as compared to the galvanized type of the tubes. Compact in design, thereby occupy less cold room space. Weight is only about 40% of the conventional galvanized type of the tubes. Refrigerant charge is lower by about 35%. Less energy consumption due to the shorter defrosting cycle and no corrosion, and there is a longer shelf life. So there is a recommendation that we should use, instead of this galvanized type of the tube, we should use the SS type of the tubes. Next, please. Then again, fanless cooling towers, which is induced draft jet type of FRP cooling towers, are another innovations. The air movement in this type of cooling tower is created with the help of the water jet, which eliminates the need for the fan to create the air draft and thereby resulting to saving on the power. See, there is no moving parts, the maintenance required in the minimum, and also the prolong the life of the cooling tower. So we recommend that we should have a fanless type of the cooling towers. Next, please. Now, aqua ammonia respiration systems, which is a absorption type of the cycles. The absorbent is a aqua ammonia liquid, absorb the ammonia vapors from the chiller. The resultant aqua ammonia strong solution liquid is then pumped to the higher pressure using the pump and a smaller electrical motors. So when you use this aqua ammonia processing system, your power consumption goes substantially down. Next, please. Being a compressible, the compression of the gas is more energy intensive compared to the liquid, which is generally incompressible when we are talking about ammonia, liquid ammonia, gas system can be compressed using the pump. The high pressure liquid is then heated to release the absorbed ammonia back to the condenser. The heat is usually from the steam, but in practice it can be also any form of the steam, which is generally available in our dairy plants. Next, please. Now, this is what I tried to show you, the solar aqua ammonia absorption refrigeration plant, which is common in other countries also, where the energy is also taken from the sun. And they say all absorption cycle is shown here, where the cooling of the milk can be taken. You can see the evaporator, absorbers, heat exchangers, generator, condenser, and the receivers. And the power, the solar heating is also coming up as a source of energy. So these are some of the absorption systems which is commonly getting now utilized instead of the compression systems in the dairy plants. And I think Thermex is also doing a lot of work on this direction. Next, please. Now these are some of the advantages I have shown as compared to the compression systems with the absorption. Reduction in the dependence on electricity up to the 90% with a very little maintenance and the spares requirement. Sub-zero temperature right to the minimum, minus 30 degrees centigrade is possible without going into vacuum. Flexibility in desired temperature possible without going into the vacuum. Flexibility in desired temperature possible without reduction in the plant capacity. Simple, noiseless, and vibration free. So there are no any moving parts in this type of system. So maintenance others can be also reduced. So next, please. I just given some of the comparison here with the compression systems where the requirement for the 1 lakh liter dairy plant, the kilowatt requirement about 310 on the right hand side on the top. And if you see the aqua ammonia absorption requirement is only 75 kilowatts. So other parameters are C, but you can see the total cost per year is coming about 22 lakhs. And when you compare with this other cost is coming only 20 lakhs. So when you use the absorption system, that is a lot of advantages are there, and whatever the energy is available, either through solar or low pressure steam, which can be utilized as a heating media. So this can become more popular now, and it is a very much energy saving technology. Next, please. Now we talk about the steam, which is also a big requirements, and mainly we are getting for the oil, gas, and coal, which is also reducing the limited energy resources put pressure on the industries to tap various renewable energy resources to minimize the dependence on this conventional fuel. As the same is not going to last longer. So we should have some other options. Can I have next, please? So we are just now, I think our earlier speaker also gave a lot of emphasis on the solar heating system. Solar heat is one of the promising renewable energy resources which is freely available in abundance. Moreover, it is eco-friendly as there is no emission of the greenhouse gases. Most of the parts in India receive the solar radiation at the rate of 5 kilowatt per day per square meter. So a lot of potentiality there in our India, particularly when we have got hot climate, utilize the solar energy. And mainly we are utilizing wherever there is a heating is required. Can I have next slide, please? Solar energy, various heating applications are already being used in some of the dairy plants for reducing the fuel bill. Hot water up to 80 degrees centigrade can be obtained from the solar water heaters, which can be conveniently used for the crate washing, can washing, CIP system, preheating, boiler feed, etc. So this type of energy can be also generated through the solar heating system. Next, please. Now we are talking about the high efficiency boilers, which is generally available in India. We get the efficiency about 86 to 88%. However, by using the continuous modular type of the burners, the thermal efficiency of this boiler has been improved to 90%, thereby reducing the fuel cost and also conserve the fuel. So basically, we are talking about utilizing the continuous modular burner systems in the boilers, which will improve your efficiency of the boiler up to 90%. Next, please. Now, also we are using the air heaters in our spray drying plants for the drying of the malt, which is heated up to the help of the steam radiators or the thermal oil radiators. However, the 10 to 50 energy saving can be achieved by using the directly fuel-fired air heaters in place of the steam radiators, and 15 to 20% saving is by replacing the thermal oil radiator. So once we have a direct purified air heaters, direct purified air heating systems, so a lot of the saving is there as compared to the normal heating system. So this is some of the advantage we should take. Next. Now, hot water based system also we are recommending, because we find that a conventional steam distribution system, on account of the steam leakage and the condensate, the drain is about 30% in the typical dairy plant. This can be reduced to a large extent by using the hot water based heating system in place of the steam boilers. The initial cost and the operating cost of the hot water systems are also relatively lower compared to the steam boilers. Next, please. Now we are using the water also we have mentioned earlier also. So these are some very much using for heating, cooling, or clean up, everything is required. So generally we are using water requirement has gone down substantially, 0.8 to 1 liter per liter of the milk process. But if you use in the automatic dairy plants, where consumption is kept at 0.5 to 0.8 liters per liter of the milk process. Water condensate could be also collected and reused in the day. Whatever the condensate collected in the dairy plant can be used, either putting with the back to the boiler for heating. So processed water has to be substantially reduced. Next, please. Then again about the compressed air. Again we are talking about this. Reciprocating air compressors are generally used in the dairy plant for supplying the compressed air. However, the now new screw compressors are being preferred over the reciprocating compressor in the case of varying the load, because of the full load power requirement of the screw crank ranges from 0.35 to 0.4 kilowatt per liter per second, as compared to the 0.38 to 0.43 liter kilowatt second in case of a single stage reciprocating. So we recommend strongly that we should use the compressor screw type of the compressor, particularly in the compressed air section. Next, please. Now, energy conservation, I will talk about the product and process manufacturing. This was earlier, I just covered mainly the utilities where we can cut down the cost and the energy. Now, next, please. Now, we are talking about the bulk milk coolers. Bulk milk coolers are with the direct expansion system consumes about 15% less power as compared to the chilling of the milk using the conventional ice band system. So we recommend there should be a direct expansion system instead of the IBT systems in the bulk milk coolers, which will save you about 50% less power. This is also one shown solar milk cooler. You can see that solar panels are there on the top on the right side, and that the batteries are charged. And through this bulk cooler, the battery can run you can keep it, charge it, and then you can use this bulk cooler for cooling of the milk. So this is also now becoming very common, and many places I've seen this type of operation has started. So this is a good thing, and this is batteries are charged in the daytime, and then it can run, and you can have a directly expansion systems here also, where you can cool down the milk instantly in the BMC, the solar system. Next, please. Now these are also some of the work has been done by the Rajasthan Electronics at Jaipur about the solar BMC. So you can see that here is all the reflect panels are there. Through that batteries are charged, and then this can be run on the batteries. So this is also a lot of saving of energy happens in the BMC. Now these are some of the cost involved to making the solar power BMC. We have got three capacity: 500 liters, 1000 liter, and 2000 liters. So this is the Rajasthan Electronics has developed now systems which will cost additional cost more than the BMC plus this cost of the getting the rooftop type of the solar power system. By this addition of the cost, maybe 2-3 lakh rupees more, you can have a completely solar power BMC and can be independent. You don't have to worry about the power interruption. There is no electric bill. So this has to be promoted in a big way to have a solar power systems wherever it's possible. Next, please. Now we'll talk about the milk processing plant. Here also, generally we are keeping pasteurization plant designed for the 90% efficiency. But if you want to increase the efficiency by putting the more plates, then a lot of the saving of the energy takes place. Can I have next slide, please? Now this is I have shown on the left side when you can have a regeneration efficiency in the pasteurization plant. 85%, 90%, 93%. When you increase the efficiency of the lot of running cost has been substantially on the right hand side, you can see it has gone down. So better to have a more regeneration efficiency and putting the plates or designing accordingly. This is mainly happening with our motor, mainly on automatic plants. But if you can get the 90% efficiency, regeneration efficiency, lot of running cost saving is there. So a lot of steam requirement also, everything is reduced. You can see on the second column also, in water requirement also goes down when the efficiency of the regeneration is increased from 90 to 93%. Next, please. Now, self-cleaning separators also now becoming very much common in India, which is basically for the fat loss in the skim could be brought down to about 0.08%. The following example illustrates the potential of 10,000 liter capacity self-cleaning work out to be like this. How much fat losses will be reduced in terms of 8 kilos fat losses per day, 128 kilos fat losses per year. So these are some of the losses. Anyhow, it goes to the skim milk, but these are some of the fat can be saved if you have got the self-cleaning separators, which is now becoming very common. Generally, we used to use a manual type, but this will save a lot of fat in the milk. Next, please. Osteo standardization unit plays an important role in minimizing the losses of the valuable fat and SNF in the dairy processing. Online analyzing and auto correction makes it possible to blend the fat and SNF accurately and uniformly, which is not possible using the traditional batch operation method. So this auto standardization method is very much good to control the fat and SNF very accurately, and that you can minimize the losses. Next, please. Process automation is now latest available. Most of the dairy plants are going for this automation, which will reduce on the sort of a completely manual controls will go away. An automatic control like PID controllers, flow controller, etc., can replace the manual controls for timing and controlling the heating and the cooling processes. So process automation is very important in the dairy plant. Wherever it's possible, we should try to achieve it. Next, please. These controls not only reduce the costly energy wastage, but also produce the added bonus of improved and uniform product quality, reduction in the process losses, high degree of hygiene, increase the productivity and flexibility, reduction in the manpower requirement. So once you put the plant in automation, a lot of advantages are there in terms of manpower requirement, for consistent quality you get it, and the minimum product losses will be. Next, please. Now, I also just seen one or two plants compare with this before automation and after automation, how much saving is there. You can see in the first plant, water consumption also has gone down. 20% saving is there. Electric consumption also has gone down, and a furnace oil requirement is also there. So you can see this is just a summary to give you an idea. By the automation, a lot of reduction is there in terms of all the utilities requirement, water requirement, electricity requirement, furnace oil requirement. So we should aim as much as possible, even for the small dairy, medium dairy plant, to have a maximum automation. Next, please. Now, I just again narrated what are the advantages. Handling the large quantities you can do online, operational flexibility is possible, consistency in quality you can get it, efficient management of the plant, minimum product losses, lower chemical taste, can do it. Energy conservation will be there, real-time data management and inventory control. These can have a better control when you got automation in the dairy plant. Next, please. Now we will talk about some of the continuous line. Rather than a batch process, reduce the frequency of cleaning and the utility consumptions. Next, please. Now this is, I have shown some very old, what we had earlier to making of the coa, if you see on the left hand side and on the right hand side. When you have got a wood fire, the cost is 10.55 rupees, and wood and kerosene and steam jacket rope or direct diesel fired and NGDB designed continuous coa plant. So you can see the cost of labor utility coa goes down as you improve the semi-automatic or more hygienic or continuous type of the coa plant. So I think in India we are also big manufacturing of the coa, but still we don't have a much continuous coa plants in a commercial way. NDRI, NDDB, so many has developed, but it has not been commercialized. So a lot of the saving of the will be there in terms of the labor, in terms of the what you call utilities, everything. So better to aim for a traditional product, we can have a very consistent quality of the products. Yes, please. So this is the old one line diagram. I have shown it for making the continuous coa plant, which is not much commercialized. Maybe some technical consistency problem, but this has to be studied at SMC college also, at NDDB also. So it requires some more on studies. But if you can make the continuous coa consistent quality, you can have save a lot of energy, manpower, space, etc. Next, please. Now, continuous butter churn also now becoming very common in India with the higher capacity, which are they are more energy efficient. They can produce butter having a low moisture content. That is also can have better control of the moisture and salt also. They reduce the losses of the fat in the butter. So propose let us plan for that. Mainly the continuous butter churn type of the instead of the batch type of the butter churn, where you can have a better quality of the products. Next, please. Now we are talking about some of the evaporator and the spray drying plants. We have shown that if you have got single effect, 2 effect, 3 effect, and 4 effect evaporating plant, mainly for the making the milk powder, evaporator in the spray and drying plant. You can see that when you are required, you see third column, you can see that when you have a single effect, the steam requirement is 1.1, and if you got 2 effect, it becomes less than half, and third it becomes 0.25 to 0.3. And 5 effect 0.14. So by addition of this, all this effect more in the evaporating plant, falling film evaporator, the steam requirement, energy requirements go substantially down. So we have to optimize, we have to, plant design in such a way that we can have at least 2-3 effect evaporator for a medium dairy plant. Next, please. Now, two-stage drying plant consumes 10% less heat in comparison to the single stage dryer. In case of the two-stage drying plant, there is also possibility to limit the stack losses to 0.1%. You can reduce the stack loss once you got two-stage dryer. The economy can be further improved by increasing the inlet air temperature or the feed consumption. So capacity of the two-stage dryer can be also increased, and the stock losses could be also reduced. Next, please. 3-stage dryer also, which gives you high quality powder with low energy consumption. So this is a very much now very common in India, 2-3-stage dryer, which has to give better quality product with a lower energy requirements. Next, please. Then we can have also bag filters. Sanitary bag filters are also being used to receive the powder fines escaping through the exhaust air from the cyclone separator. So this also save a lot of air pollution and the recovery of the milk solids to the big filters, bag filters. So sanitary bag filters has to be installed whenever it's required. Next, please. Now energy conservation I have talked about in the milk packing area. Yes, please. Next one. Here I have compared about this our foam fill seal machines, which is used mainly for the liquid milk filling in our dairy plants. We have got 2 types. One is a requirement is for this One is with a mechanical type and one is a air compressor type. Most of the dairy plant is now replacing the air compressor type of the compared to the mechanical type of the pump seal machine. You can see that power requirement in the first column also 7 kilowatt requirements with the pneumatic type, where the mechanical type of the pump seal require 3.5 is required. So a lot of saving is there in terms of accuracy also, filling accuracy also, in terms of cost also. So we recommend that we should have a minimum, we should go with the mechanical type of a form fill seal machine as compared to the pneumatic type of the form. Next, please. Now also we can save a lot of in the packaging film also with the technical development in the blower film process coupled with the availability of the high performance polymers. It would now be feasible to manufacture high strength wood quality film which minimize the thickness variation. This can not only help in downing the gauging of the packaging film thickness, but also reduce the film consumption by about 20%. The right type of the thickness, right type of the quality is very important to reduce the requirement of the film, and it can also cost down. Next, please. I just shown the loss identification, prevention, and control programs for any dairy plant to apply. So first you have to visualize what are the areas of the losses. Then compare with the SAT norms. You have got some SAT norms or government also some SAT norms. A lot of things are available. Then you have to see quantify the losses, analyze the process or operations critically, then identify the critical points, evolve the appropriate action plan for that, whatever requirements are there, identify the right person and assign the responsibility. Decide the responsible limit or whatever the reasonable limit for each one, execute the action plan rule, elimination of the causes, what will be the reason for this, and finally performance evaluation, and give the responsibility to the person or award for the improvement. So this is a loss identification and prevention control program is very useful for all the dairy plant to control the energy requirement, manpower requirement, and efficient production of the milk and milk products. Next, please. Now, conclusion, I want to say the energy conservation in the dairy plant is possibly by adopting the advanced processing technology, scaling up the traditional processing, use of microprocessor-based controls, training of the staff to identify, monitor, and control the sources of losses, setting up the target for yield or output, and focusing on the achievements and increasing the general awareness. Implementation of the corrective actions, operating plant at a maximum design capacity, monitoring of the waste at a routine checkup on the effectiveness of the corrective plan program, and proper technical auditing. Technical auditing of all the utilities, all the operations are very much, this can be done maybe quarterly in a year or 2-3 times in a year, and that has to be done. Next, please. So that's my conclusion. Thank you very much for your attention. And I think if anybody has got question, anything, I'm ready to answer. Thank you very much. Very nice of
you. Thanks a lot, sir, for your practical and valuable detailed information about the numerous options available for reducing energy wastage, increasing the productivity along with cost advantage in the dairy industry. Thanks a lot, sir.
Thank you.
We have been listening to the eminent speakers deliberating in the areas of reducing the carbon footprint in the dairy industry since 11 a.m. All these valuable insights have given us a new perspective that one should adopt while discussing these issues. May I now request Dr. P.R. Patel, Executive Director, MIDFT, to kindly give the concluding remarks. Sir, please.
No, I won't take much time. I would hand over to Dr. Shukla to thank everybody.
Good afternoon, all. This is a second edition of our marathon web editions on the topic that is reducing carbon footprint in the dairy industry, future and challenge edition 2. And the eminent speaker presented so well and all the learned, enthusiastic audience continue to be with us till now. And so without taking much of the time, I'll go for the formal vote of thanks. First and foremost, I am grateful and thankful to our Honorable Vice Chancellor, Professor Dr. Anish Keelawala, who has been with us today and every day for motivating all the events at MIDFT and development activities. Even for his busy schedule, he has taken out time to be with us. And at present, he is moved to Sachivalaya as our Dr. P. Patel inherited that there are amalgamation of so many colleges within the Town University. So thank you, sir, very much for supporting MIDFT and being with us in all of our events and presently today to have giving the inaugural remarks. Further, I am thankful to Professor Dr. G.S. Rajoria, President Indian Dairy Association, who consented warmly to deliver a keynote address to this August gathering. Thank you, sir, for being with us. I am also thankful to our learned speaker, Dr. Sulindra Tati, CEO, Prompt Innovations, Professor Manishankar Dasgupta, Head Mechanical Engineering, from BITS Pilani, Mr. Priyank Mehta, Executive Engineer, Banas Dairy, and Dr. J.V. Parekh, whom we recently heard, Dr. Dairy Consultant and Technical Advisor for Dairy IDA, based at Mumbai. Apart from that, I am very much thankful to all other participants, particularly deans and directors of Kamden University, other state agriculture universities now being a part of Kamden University, Dr. J.P. Prajapati, retired principal and dean of SNC College, Dr. Patil, President IDA West Zone, and all other learned speakers. I am also, and participants, I am also thankful to the viewers and audience from all over the corner of India, from different colleges, dairies, private organizations to be with us. And finally, I am thankful to our Executive Director, Dr. P.R. Patel, for motivating us to continue for such managing the events and all the support, along with my colleagues, coordinators, and team MIDFT. At this short juncture, I'll just make a note that you all are welcome to put your queries and questions through email or in the chat box, even in the future, and we'll be communicating all that to the speakers. The whole recorded version of this webinar and previous one are available on the MIDFT website, so anybody can just go and scroll it and scan it and can have a review on it. And we'll be waiting for you to join us for further events. Thank you, one and all. Thank you.
Thank you, sir. Ladies and gentlemen, may I thank you very much for your active participation in this webinar. I hope you all enjoyed the program, and with this motivation, we will continue to bring forward many such webinars for delivering in the area of knowledge. Thank you, one and all. With the kind permission of ED sir, Principal and Dean sir, and all the dignified personalities present with us in this webinar, may I conclude the webinar with this?
Thank you very much.
Yes.
Thank you, Bani. Thank you for everyone. Bye-bye.